Hello, today I want to share about how to compute Fibonacci numbers in O log n time complexity using matrix exponentiation. So let's first start with the basic definition. To base case if the first number is 0, the second number is 1, and every following term is just the sum of the previous two terms. And normally, to compute the nth term of the Fibonacci sequence, we do iterative or dynamic programming, and if that costs O n time complexity, what we want to do today is to achieve the O log n time complexity. And a key relationship is just to identify the Fibonacci change transition using matrix. As we can see, the action of operation of calculating next term is just the Fn plus Fn minus 1. And what we need for the next step is only Fn, and this can be transitioned to this 2 times 2 matrix. And as we know that each transition, actually the transition matrix is exactly the same. So by applying the matrix for n times, starting from the basic state, that is what we will have. With that, we can simplify the representation. And since we only care about the uh, final term, which is the n plus 1 term, and that is actually, if we just start from the base term, it's actually the top left elements of the matrix multiplication, since the matrix multiplication also has results in a 2 times 2 matrix. So we call this transition matrix M, and the nth term of the Fibonacci sequence is just the top left element of the matrix M to the power of n minus 1. So now we have converted the idea of calculating the nth term of Fibonacci into compute the power of a matrix efficiently. We can do this using recursive algorithm, like split the exponents by halves each time, recursively calculate the lower half, and then square the half together. Also need to apply in one next term multiplication if n is odd. So here is the pseudocode for the quick power using recursive algorithm. Basically just what we described above. So using that fast power, we can construct our Fibonacci algorithm, which has the base case where n equals to 0 and we return 0. Then if for the more following terms, we define the matrix M and apply the fast power, then simply return the top left element. And that is the algorithm for the fast Fibonacci calculation. The time complexity is log n, and its base complexity is a 1. Next, let's look at an example about applying this algorithm. So let's say we want to calculate the 6 terms of the Fibonacci sequence, which is we just calculate the uh, matrix M to the power of 5. In this case, first is M squared, and then M to the power of 4. And since the answer we need is the M to the 5, we need to add another multiplication on the base of M to the power of 4. And as we can see, the top left element is 8, and it conforms with what we need, which is the 6 terms of Fibonacci sequence. So here comes this conclusion. The core idea is we represent Fibonacci using matrix exponentiation, and then use recursive exponentiation to compute powers in the log n complexity. Also, what's interesting is that this can be generalized to other linear recurrences with constant state transitions. And here is the final conclusion with the base case and the elegant, efficient, and mathematically beautiful representation of the nth term of the Fibonacci sequence.